Hello everyone, my name is Harivansh Dogne and today we are going to solve the interview question and answers related to regression model evaluation and handling imbalanced data. So let's start. So one of the most important question in any machine learning interview is once you've built a regression model, how do you know if it's actually good? That's exactly what evaluation metrics are for. Let's walk through the 5 key metrics you absolutely need to know. The first one is MAE, which is mean absolute error. This is the simplest one to understand. You take the difference between the actual value and the predicted value for every data point. Ignore whether it's positive or negative. That's what the absolute value does. And then take the average. So if your model predicts house prices and is off by $10,000 on average, your MAE is 10,000. Simple, intuitive, and easy to explain to anyone. The one downside is that it treats all errors equally. A small error and a huge error get the same treatment. Next is MSE, which is mean squared error. Instead of taking the absolute difference, MSE squares the errors before averaging them. Why does squaring matter? Because it punishes larger errors much more heavily. If your model makes one giant mistake, MSE will flag that very clearly. This makes MSE useful when large errors are especially bad in your use case. The downside is that the value is now in squared units, which makes it harder to interpret directly. That's why we have RMSE, root mean squared error. RMSE is simply the square root of MSE. By taking the square root, we bring the metric back to the original unit of measurement. So, if you are predicting house prices in dollars, your RMSE is also in dollars, making it much easier to interpret. RMSE is arguably the most widely used regression metric in practice because it combines the sensitivity of MSE with the interpretability of MAE. Now R square score, also called R squared or the coefficient of determination, this metric answers a different question. How much of the variation in the output does my model actually explain? R square range from 0 to 1 and R square of 1 means your model perfectly predicts everything and R square of 0.85 means your model explains 85% of the variance in the data, which is quite good. And R square close to 0 means the model is barely better than just predicting the average time. But here's the catch. R square has a flaw. Every time you add a new feature to your model, R square will either stay the same or go up, even if that feature is completely useless. This can give a false impression that your model is improving. That's where adjusted R square comes in. It adjusts the R square value by penalizing you for adding features that don't actually help. If you add an irrelevant feature, adjusted R square will go down. So when you are comparing models with different numbers of features, always use adjusted R square, not plain R square. Now we come towards handling imbalanced data. Now let's talk about a very common real world problem, imbalanced data. Here's a situation. Imagine you are building a model to detect credit card fraud. Out of 1 lakh transactions, maybe only 200 are actually fraudulent. That's just 0.2% of the data. If your model simply predicts not fraud for every single transaction, it will be 99.8% accurate, but it will catch zero frauds. That's a disaster. This is the imbalanced data problem, and knowing how to handle it is a critical skill. Let's go through the 5 main techniques. The first is oversampling with smooth, which stands for synthetic minority oversampling technique. Instead of just duplicating existing minority class samples, which can lead to overfitting, Smooth synthetically generates new samples by interpolating between existing minority class data points. This gives your model more examples of the rare class to learn from without simply copying the same records. Next is undersampling. The opposite approach here, you reduce the number of majority class samples to bring it closer to the size of minority class. It's faster and simpler, but you do risk losing useful information from the majority class. The third technique is class weighting. Instead of changing the data, you tell the model, pay more attention to mistakes on the minority class. You assign a higher loss penalty for misclassifying underrepresented samples. Most machine learning libraries support this directly through a class weight parameter. Fourth is data augmentation, creating variations of existing minority class samples through transformations like flipping, rotating, or adding noise, particularly useful in image or text classification tasks. And fifth is ensemble methods, combining multiple models together, like using balanced random forest or easy ensemble, which are specifically designed to handle class imbalance by sampling balanced subsets during training. Now let's look at the three Python frameworks commonly used for this. PyTorch gives you maximum flexibility. You can write custom loss functions that weight classes however you want, and its dynamic computation graphs make experimentation easy. TensorFlow is Google's scalable ML framework and has built-in support for class weights along with powerful data pipeline tools that make handling large imbalanced data sets more manageable. And scikit-learn is your go-to for classical machine learning. It offers pre-processing utilities, resampling tools often used alongside the imbalance learn library, which integrates seamlessly with it, and evaluation metrics specifically designed for imbalance classification like classification report, precision recall curve, and F1 score. So the golden rule to remember is accuracy is a misleading metric for imbalanced datasets. Always evaluate your model using precision, recall, F1 score, AUC ROC curve. This tell you the real story. Thank you.